Ancient builders achieved engineering feats that seem impossible even today. This video uncovers the 25 lost methods they used, secrets that modern scientists are only now beginning to understand. You will discover how forgotten innovations from the Romans to the Mayans are providing brilliant solutions to our own modern problems. How did concrete heal its own cracks for 2,000 years? What mysterious substance allowed fire to burn on water? By the end, you will see the ancient world not as a graveyard of forgotten ideas, but as a living library of inspiration for our future. What forgotten marvel from the past most captures your imagination? The grandeur of Rome did not fade quietly into the night. Instead, its decline marked the beginning of a long, slow vanishing of knowledge that would set humanity back for centuries. With the empire's collapse, the intricate trade networks and administrative systems that supported master builders and engineers simply fell apart. This was not an isolated event. The legendary Library of Alexandria, a repository for countless scrolls containing the world's most advanced understanding of mechanics, mathematics, and construction, was lost to fire and conflict. These were catastrophic blows to human progress. Suddenly, the sophisticated methods for creating self-healing concrete, forging superior steel, and designing complex machinery were no longer being taught or practiced. The very knowledge that built aqueducts and monumental structures faded from memory, leaving behind silent, crumbling giants that stood as riddles for the future. We entered a profound dark age, not merely of philosophy and art, but of practical, world-shaping engineering. Societies that followed were forced to reinvent even the most basic technologies, a painstaking process that took hundreds of years. The sheer scale of this loss is almost incomprehensible. It left behind magnificent monuments and a handful of cryptic texts that we are only now, with our advanced tools like three-dimensional scanning and material analysis, beginning to fully decipher. This context of profound loss makes the modern rediscovery of these ancient methods so breathtaking. It is not merely an academic exercise. It is the recovery of a lost heritage, a second chance to learn from the brilliance of our ancestors. This backdrop of a world forced to start over makes the discoveries we are about to explore feel all the more miraculous. Those silent harbors held a secret within their submerged walls. For 2,000 years, structures made of Roman concrete have not just endured the relentless sea, they have grown stronger. This defies everything we know about modern construction, where saltwater is a primary enemy, relentlessly corroding and weakening our own concrete within decades. The question of how these ancient piers and breakwaters achieved such longevity baffled engineers for centuries. The answer, hidden in the very fabric of the material, was only uncovered with the power of advanced microscopes. Researchers discovered tiny, white chunks known as limeclast scattered throughout the Roman mixture. For a long time, these were considered a sign of poor mixing, a primitive mistake. The truth is far more brilliant. These limeclasts are actually the concrete's self-repair system. When seawater seeps into a tiny crack, it reacts with the lime, triggering a chemical process that forms new crystals of calcium carbonate. These crystals expand, seamlessly filling the fracture from the inside out. The concrete literally heals its own wounds. This was not an accident. It was a deliberate, sophisticated engineering feat lost to time. Today, scientists are racing to reverse engineer this ancient wisdom. The goal is to create a new generation of concrete that can repair itself, drastically cutting down on the monumental environmental cost and constant disruption of rebuilding our crumbling bridges, roads, and tunnels. This single rediscovery shifts our entire perspective. It reveals that the path to a sustainable future might not lie in ever more complex new materials, but in understanding the profound, elegant simplicity of an ancient one. From the self-healing stone of the harbor, we turn to a discovery pulled from the depths of the sea. A single, encrusted artifact recovered from an ancient shipwreck near the Greek island of Antikythera appeared at first to be little more than a lump of corroded bronze and wood. For decades, it sat in a museum, its true nature a complete mystery. Then, researchers began to peer inside using advanced X-ray technology. What they found was breathtaking. Hidden within that unassuming crust was the most sophisticated mechanical device known from the ancient world, an intricate system of precisely cut bronze gears, some with teeth finer than a millimeter. This was the Antikythera Mechanism. It was, in essence, an analog computer crafted over 2,000 years ago. By turning a hand crank, an operator could make this device calculate the movements of the sun, the moon, and the known planets across the sky. It could predict lunar and solar eclipses, and even account for the subtle wobble in the moon's orbit, a phenomenon known as precession. The complexity of its design is staggering, featuring a form of differential gearing that was thought to have been invented in the 14th century. This single device rewrites our entire understanding of ancient Greek engineering. It proves they possessed a level of mechanical sophistication that historians never dreamed possible for that era. The mechanism stands as a silent testament to a lost pinnacle of technology, a branch of knowledge that was almost entirely erased. Today, scientists are not just studying it as a historical curiosity. They are looking to its principles for inspiration. The device is remarkably compact, robust, and entirely mechanical. This makes it a potential blueprint for new kinds of computers designed to operate in extreme environments, like the deep sea or the vacuum of space, where delicate electronic systems can fail. The Antikythera Mechanism is more than a relic. It is a challenge from the past, a brilliant puzzle that continues to offer solutions for our own technological future. High atop the Andes, the stone walls of Machu Picchu stand as a silent dialogue with the mountains themselves. These structures, assembled from colossal blocks cut with impossible precision, have withstood centuries of violent tremors that would reduce modern buildings to rubble. Their secret lies not in rigid strength, but in a brilliant, flexible design. The Inca builders intentionally shaped each stone into a complex polygonal puzzle, fitting them together without any mortar. During an earthquake, these interlocking blocks do not fight the force. Instead, they dance, they shift, rock, and settle against one another, dissipating the tremendous energy of the seismic waves. Once the shaking stops, the stones simply settle back into their original positions, locked together once more. Modern engineers now recognize this as a masterclass in managing dynamic loads. The Incas, without any formal knowledge of physics, intuitively understood a principle that is revolutionizing modern construction: base isolation. This contemporary method involves placing flexible bearings or pads between a building and its foundation, allowing the structure to move independently from the shaking ground. It is the same concept the Incas carved into granite. Today, this ancient wisdom is directly informing the design of hospitals, schools, and skyscrapers in earthquake-prone cities around the world. The legacy of these master stonemasons teaches us a profound lesson: that true resilience is not about resisting immutable forces, but about learning to move in harmony with them. While the Incas mastered the Earth's movement, another civilization sought to command an even more fundamental force. The Byzantine Empire protected its shores with a weapon so fearsome its formula was a secret worth more than gold. From the prows of their warships, they unleashed a stream of liquid flame that could not be extinguished by water. Historical accounts describe it clinging to ships and men, creating a blaze that danced across the waves, a psychological and tactical advantage that secured naval dominance for centuries. The precise recipe was so closely guarded that it vanished completely, becoming one of history's most enduring chemical mysteries. For generations, the very nature of Greek fire was pure speculation. Today, by carefully analyzing ancient texts and studying chemical residues from artifacts, researchers have pieced together a plausible hypothesis. They believe it was a complex, napalm-like mixture based on crude petroleum, likely enhanced with quicklime, a substance that reacts violently with water, generating intense heat and potentially igniting the fuel. Other ingredients like resin or sulfur could have made it more sticky and difficult to smother. This was not simple oil on fire. It was a sophisticated, pre-mixed chemical weapon designed for a single, terrifying purpose. The quest to understand Greek fire is not about recreating its destructive power. Instead, scientists are fascinated by the chemical reactions that made it so persistent. How did it achieve such a sustained and uncontrollable burn? The answers to these questions are proving invaluable in a completely opposite field, fire suppression. By understanding the precise mechanics of how such a fierce fire worked, we can design far more effective ways to stop modern blazes. The same principles that made a flame cling to water could lead to advanced firefighting foams that smother flames more completely. This ancient weapon, born from conflict, now pushes the boundaries of materials science, showing that the line between a tool of war and a tool of safety is often blurry. Unlocking its volatile secrets may one day give us new thermal materials with perfectly controlled burn properties, turning a historical instrument of fear into a potential guardian of life. Beneath the sun-scorched plains of ancient Persia, a hidden river flowed in perfect silence. This was the Qanat, a marvel of hydro-engineering that turned deserts into fertile gardens. While other empires built monuments to the sky, Persian engineers looked downward, mastering the earth itself to sustain life. Their method was one of profound patience and insight. They began by digging a mother well deep into the foothills of a mountain, reaching a hidden aquifer. Then, with an almost supernatural understanding of the land's gentle slope, they would dig a gently sloping tunnel backward for dozens of miles, sometimes even further, to their city or farmland. A series of vertical access shafts were dug along the tunnel's length, not only for construction and maintenance but to allow cool, clean air to circulate. The water flowed entirely by gravity, emerging at the surface as a steady, reliable spring. This was not a forceful extraction of water. It was an invitation, a careful channeling of the Earth's own bounty. The genius of the Qanat lies in its passive efficiency. Because the water travels underground, it is completely protected from the evaporating heat of the sun, a critical advantage in an arid climate. There are no pumps, no external power sources, just the unwavering pull of gravity and the wisdom of a gentle slope. For centuries, this network of hidden veins sustained entire civilizations in places where surface water was a fleeting dream. Today, hydrologists and urban planners are looking back to this ancient system with renewed respect. In a world facing growing water scarcity, the Qanat offers a blueprint for sustainable distribution. Modern solutions often rely on energy-intensive pumps and surface canals that lose vast quantities of water to evaporation. The Qanat, by contrast, is a model of resilience. Its principles are now being integrated into green architecture and landscape design, inspiring systems that harvest and channel rainwater passively, reduce reliance on complex infrastructure, and recharge depleted groundwater. This ancient method teaches a lesson we desperately need to relearn. The most advanced engineering does not always mean overpowering nature. Sometimes it means listening to the land and finding the most elegant path for its gifts to flow. The silent precision of the Great Pyramid of Giza confronts every visitor. Its four sides align almost perfectly with the four cardinal directions, north, south, east, and west, with an error of less than 1/15 of a single degree. For centuries, this accuracy presented a profound mystery. How could a civilization without magnetic compasses or satellite guidance achieve such geometric perfection on a scale of millions of stone blocks? The answer, it seems, was written in the stars all along. Archaeoastronomers, scientists who study how ancient cultures understood the sky, have proposed a brilliant method. They suggest that Egyptian surveyors used a simple wooden sighting tool to track the path of two specific stars as they circled the celestial pole. On one special night each year, these two stars would cross the meridian simultaneously, one directly above the other in a perfect vertical line. By bisecting the angle between their rising and setting points, the builders could trace an impeccable true north-south line across the desert. This technique, verified through sophisticated computer models that recreate the ancient night sky, reveals a staggering depth of astronomical knowledge. It was a practical, elegant solution that turned the heavens into a master blueprint. This ancient celestial wisdom is now finding new life in our most advanced technologies. The same principles of stellar alignment are being studied to improve the calibration of Earth observation satellites and to refine long-range surveying methods where GPS signals are unreliable. The pyramids, therefore, were far more than royal tombs. They were monumental compasses and stone calendars, physical embodiments of a philosophy that saw no separation between the Earth and the cosmos. Their enduring silence challenges us to remember that some of the most powerful engineering tools are not in our hands, but are forever orbiting above our heads. From the silent stability of the pyramids, we find an ancient device that listened for the Earth's deepest tremors. In 2nd century China, the brilliant scholar Zhang presented the court with a masterpiece of art and engineering, a large bronze urn encircled by 8 dragon heads, each holding a bronze ball. Below them, 8 corresponding frogs waited with open mouths. When an earthquake struck hundreds of miles away, the device would reportedly come to life. One dragon would release its ball, which would clatter into the frog's mouth below, indicating the precise direction of the distant quake. For generations, this account seemed more like legend than science. How could a mechanical object detect something so subtle and far away? The secret lay inside the beautiful urn. Modern reconstructions suggest a heavy, inverted pendulum was suspended at its center. When seismic waves traveled through the ground, the pendulum would swing, striking a lever mechanism that directed one specific dragon to open its jaws. This was not magic. It was the world's first functional seismoscope, a device that detected the arrival of earthquake waves. Its principle of operation, an inertial sensor isolated from the shaking of its own casing, is the very same concept used in modern seismometers. The elegant genius of Zhang Heng's device is now inspiring a new wave of research. Scientists are exploring how its simple, robust, and power-free design could be adapted to create low-cost seismic monitors for developing nations, places where expensive electronic networks are not feasible. This ancient invention proves that profound understanding does not always require complex circuitry. Sometimes, the most reliable guardian against natural forces is a silent bronze dragon, waiting patiently for a tremor it can feel but we cannot. Those ancient roads were built not for years but for millennia. Beneath the surface of a modern highway lies a hidden echo of Roman genius, a layered foundation that has supported traffic for 2,000 years. While our own asphalt often cracks and crumbles under the stress of seasons and heavy loads, these ancient thoroughfares endure. Their secret was not a single material, but a complete system, a masterclass in thinking in layers. Roman engineers began by digging a deep trench and packing it with a layer of large stones. On top of this, they laid successive strata of smaller stones, gravel, and sand, each compacted into a solid mass. The crowning glory was the surface itself, massive, carefully fitted blocks of hard volcanic rock. These stones were not mortared in place. Instead, they were shaped to fit together like a puzzle, creating a flexible pavement that could shift slightly with the ground beneath it without shattering. This design allowed the road to breathe, to expand and contract with temperature changes, and to drain water efficiently through the gaps between stones and down through the porous layers below. Water was the enemy they understood perfectly, and their entire design was a war against erosion and frost damage. Today, civil engineers are looking back at this flexible pavement concept with a sense of rediscovery. Our modern roads, with their rigid, monolithic asphalt surfaces, are prone to cracking under repeated stress and freeze-thaw cycles. These cracks let in water, which freezes, expands, and creates the potholes that plague our commutes and cost billions to repair every year. The Roman approach, with its flexible, multi-layered structure, distributes weight more effectively and handles ground movement far better. By integrating these ancient principles, we are now developing new composite road designs that combine modern asphalt with more flexible, resilient bases. This is not mere imitation. It is an evolution using 21st century materials science to achieve a 2,000-year-old standard of durability. The legacy of these roads is a powerful reminder that the most effective engineering creates a symbiotic relationship with the environment, working with natural forces rather than fighting them. It is a lesson in building for the future, written in stone beneath our very wheels. A Viking shipmaster could navigate through thick, impenetrable fog by holding a translucent crystal to the sky. This legendary sunstone, long dismissed as mere myth, was a genuine tool of extraordinary precision. At the heart of this method was a specific type of calcite crystal known as Iceland spar. When you look through this crystal, you see a double image, but its true magic is revealed when you rotate it. On a cloudy day, when the sun is just a diffuse glow hidden behind the overcast, the light penetrating the atmosphere becomes polarized. The Iceland spar crystal interacts with this polarized light by rotating the stone until the two images seen through it merge into one of equal brightness. A navigator could pinpoint the exact position of the hidden sun, establishing a reliable reference point for steering. This was not guesswork, it was applied optical physics, a sophisticated understanding of light that should have been centuries beyond their reach. Modern science has confirmed the method's stunning accuracy, capable of locating the sun to within a single degree. This lost art of celestial navigation is now inspiring a new generation of technology. Researchers are developing advanced polarimetric navigation systems based on this very principle. These systems offer a crucial failsafe for pilots and sailors, a way to navigate when global positioning systems are jammed, fail, or are simply unavailable. The Viking Sunstone proves that the most resilient technologies are often those that work in harmony with the fundamental properties of the natural world. It is a profound reminder that true ingenuity lies not in the complexity of the tool, but in the depth of understanding behind its use. That legendary blade, with its flowing, watery patterns, was more than a weapon. It was a mystery written in metal. For centuries, the secret of forging true Damascus steel vanished, leaving behind only the legend of swords that could slice through a silk scarf in midair, yet bend nearly in half without shattering. The steel's origin was not Damascus itself, but ancient India, where a unique process created an ingot known as Wootz steel. The method for making it was lost by the 18th century, and every attempt to recreate the metal failed. Modern science, armed with electron microscopes, finally peered into the soul of the steel. They discovered that the smiths of old were, in a very real sense, nanotechnologists. The beautiful patterns were not merely decorative. They were the visible signature of an incredibly sophisticated internal structure. The Indian method involved melting iron with specific carbon-rich materials in a sealed crucible, then cooling it with agonizing slowness. This precise thermal recipe caused the formation of carbon nanotubes and incredibly hard carbide nanowires within the softer steel matrix. Think of it as a microscopic forest of unimaginably strong fibers woven directly into the metal. This nanostructure gave the blade its paradoxical qualities, the hardness to hold a razor edge combined with the flexibility to absorb immense impact. Today, the rediscovery of this ancient process is revolutionizing material science. The principles behind Wootz steel are guiding the creation of a new generation of super-strong, lightweight alloys. These advanced metals are destined not for swords, but for the most demanding modern applications, from the airframes of aircraft and the blades of jet engines to the incredibly durable cutting tools used in surgery and manufacturing. The quest to replicate this lost art has pushed our own understanding of metallurgy to its limits, proving that the line between ancient artistry and cutting-edge science is often just a matter of perspective. The same geometric insight that gave us the arch also unlocked the vast, open spaces beneath a vaulted ceiling. In ancient Mesopotamia, where stone was scarce, builders turned to the humble mud brick. They discovered that by arranging these bricks in a curved formation, they could create a roof that supported itself. This was the birth of the true arch and its larger sibling, the barrel vault. The principle was a revolution in structural thinking. Instead of a flat beam that sags under its own weight, the curved arch cleverly redirects the load outward and downward, channeling immense forces into the supporting walls or piers. This meant interiors could be expansive and column-free, a dramatic departure from the cramped post and lintel constructions of the past. The Romans would later refine this concept into magnificent aqueducts and domes, but the foundational idea belonged to those early Mesopotamian innovators. Today, this ancient understanding of compressive strength is experiencing a powerful renaissance. Modern architects and engineers, armed with new materials like ultra-high-performance concrete, are looking back to these curved forms. They see in the arch and the vault a blueprint for material efficiency. A gracefully arched structure can often achieve the same strength as a bulky rectangular one while using significantly less resources. This is not just about saving concrete and steel. It is about rethinking our entire approach to design. The sweeping, elegant curves of modern train stations, airport terminals, and even some forward-thinking bridges are direct descendants of that Mesopotamian breakthrough. They demonstrate that the most enduring solutions are often the most elegant ones, proving that a shape discovered millennia ago in sun-baked brick continues to hold up our world, both physically and philosophically. Deep within the lush rainforest, the Maya built a metropolis that thrived for centuries. Tikal was a city of towering pyramids and a vast population, all sustained in an environment where pure drinking water should have been an impossible dream. In the wet season, torrential rains would flood the land, while in the dry season, water became scarce. Stagnant reservoirs in such a climate would have been breeding grounds for illness, a public health crisis waiting to happen. For a long time, how the Maya managed this was a mystery. Then, archaeologists excavating the city's ancient reservoirs made a stunning find. they uncovered layers of crystalline minerals mixed with coarse sand, a natural filtration system. The key ingredient was zeolite. This volcanic mineral is a molecular sieve, its crystalline structure filled with microscopic pores. As water passes through, the zeolite performs a process called ion exchange, trapping dangerous heavy metals, harmful bacteria, and other toxins within its lattice while letting clean water flow through. This is not a simple gravel filter. It is a sophisticated application of natural chemistry, a technology we use in modern aquarium and home water filters today. The Maya had discovered and harnessed this property 1,000 years ago. Their genius lay in a profound understanding of their local environment, identifying a specific volcanic rock that could solve their most critical challenge. This discovery completely rewrites our view of their civilization, revealing them not just as astronomers and architects, but as master environmental engineers. Today, this ancient method offers a powerful blueprint for our own world. Researchers are looking at zeolite and similar natural minerals to develop extremely low-cost, sustainable water purification systems. These systems could provide safe drinking water for remote communities and developing nations that lack access to complex, energy-intensive treatment plants. The Maya, by looking to the Earth itself for a solution, left behind a legacy that ripples into our future, proving that the most advanced technology is sometimes simply a matter of seeing the potential in the stones beneath our feet. A Roman merchant vessel was not merely built, it was woven together from the inside out. Its hull consisted of thousands of interlocking wooden pieces, each plank joined to the next by a precise system of tabs and slots known as mortise and tenon joints. These were then locked in place with wooden pegs, creating a single, unified shell that was both flexible and immensely strong. This monocoque structure acted like a living entity, able to twist and flex with the ocean's immense power rather than fighting it rigidly. The entire ship became a single, resilient membrane. This sophisticated approach, a pinnacle of classical shipbuilding, vanished for over 1,000 years following the empire's collapse. Its secrets were only recovered when archaeologists began studying ancient wrecks that had been miraculously preserved in silt and cold, dark waters. These time capsules revealed a construction method that, in many ways, surpassed the nailed hulls of later centuries. Modern naval architects examining these joints have come to a startling realization. The mortise and tenon system distributed stress far more evenly across the entire hull than metal fasteners, which create concentrated points of weakness prone to fatigue and corrosion. This ancient insight is now inspiring a new wave of design, not just for traditional wooden boat building, but for advanced composite materials used in modern yachts and even aerospace. The challenge of joining carbon fiber or fiberglass components often involves adhesives or metal fasteners that can fail or create dissimilar material corrosion. The principles of the mortise and tenon, a pure mechanical interlock, offer a blueprint for creating incredibly robust, all-composite structures that avoid these pitfalls entirely. This forgotten joint is more than a historical curiosity. It is a testament to a philosophy where strength emerges not from brute force, but from the elegant, interconnected unity of countless small parts. A single Egyptian obelisk represents a paradox of impossible weight and impossible grace. How do you move a stone needle as heavy as a blue whale across hundreds of miles of desert and river, then stand it upright on a tiny pedestal with nothing but ropes, wood, and human labor? This was not a one-time miracle, but a repeatable feat of logistics that modern engineers have only recently understood through careful experimentation. The journey began with a sledge, a massive wooden platform upon which the obelisk was secured. but pulling such a load directly on sand would create an immense, immovable friction barrier. The Egyptian solution was deceptively simple. They poured water onto the path ahead of the sledge. The water permeated the sand, creating a firm, slick surface that drastically reduced friction, allowing a large team of workers to pull the colossal weight with relative ease. Once it reached its destination, the even greater challenge began, raising it vertically. Researchers now believe the Egyptians used a pivoting trench. They would have maneuvered the base of the obelisk over a prepared stone foundation, with the lower end resting against a wall of sand in a deep trench. By slowly, carefully removing the sand from a special opening, the base would begin to pivot downward into the trench. This controlled descent, a gradual lowering powered by gravity and managed by counterweight ropes, allowed the monolith to swing upwards into its final, vertical position with breathtaking precision. This entire process was a masterpiece of applied physics, transforming an insurmountable task into a series of manageable, incremental steps. Today, this ancient wisdom is directly influencing modern heavy lift operations, particularly in remote or environmentally sensitive areas where cranes and heavy machinery cannot go. The principles of controlled descent and friction reduction are being studied for moving massive components for wind turbines or assembling large structures in confined urban spaces. The obelisk's silent lesson is one we are relearning, that the most powerful force in engineering is not raw power, but the intelligent application of a fundamental truth. It is a testament to the idea that any weight, no matter how immense, can be moved if you have the patience to find the most elegant path. That silent army of clay soldiers held more than spears and swords. They carried in their hands the blueprint for an industrial revolution, one that would not arrive in Europe for more than a millennium. Each of the thousands of bronze weapons unearthed with the Terracotta army, from crossbow triggers to sword blades, was manufactured with a stunning degree of precision. Their components were not one-of-a-kind artifacts. They were interchangeable. A crossbow trigger mechanism from one soldier's weapon could be fitted seamlessly onto the weapon of another, a feat that demands a rigorous system of standardized measurement and templates. This was not craft, it was organized mass production on a scale the world would not see again until the 19th century. The foundation of this achievement was a mastery of metal that defied the era. While the Western world was still forging iron in small, inefficient bloomeries, Chinese metallurgists had perfected the blast furnace. These structures, towering for their time, could reach the incredibly high temperatures needed to melt iron completely, allowing it to be poured into molds, a process we know as casting. This was a monumental leap. Cast iron is brittle, but it is also incredibly hard, and most importantly, it can be produced in vast quantities, enabling the creation of durable tools, weapons, and agricultural implements for an entire empire. The organizational genius behind this system is what captures the attention of modern industrial engineers today. They are looking past the bronze and iron to the workflow itself. How did ancient supervisors manage quality control across thousands of artisans? How did they maintain consistency in measurement without digital calipers? The answers are revealing a form of systematic thinking that is the direct ancestor of our modern assembly lines. This ancient approach to manufacturing offers a powerful alternative to our own often rigid and resource-intensive processes. It demonstrates that scale and efficiency can be achieved with remarkable flexibility, a lesson we are now applying to develop more sustainable, adaptable production methods. The legacy of those Chinese foundries is a profound reminder that the principles of quality control and standardized production are not modern inventions. They are ancient arts patiently waiting in the earth to be rediscovered. Perched high on a canyon wall, the cliff palace of Mesa Verde seems to defy gravity itself. These multi-story structures, built from blocks of local sandstone and bound with simple mud mortar, have clung to the cliffs for over 7 centuries. They have endured harsh sun, freezing winters, and the relentless passage of time. For a long time, their survival was seen as a happy accident of their sheltered location. But modern structural analysis reveals something far more deliberate. The ancestral Pueblones were not just finding shelter in the cliffs, they were engineering with them. Their walls were carefully designed to bear immense loads, transferring the weight of entire communities down through the living rock. The placement of the dwellings was a masterstroke of environmental design. They were situated beneath the canyon rim, which provided a massive stone overhang. This natural roof shielded them from summer heat and winter snow, while their southern exposure captured the low-angled winter sun for passive solar heating. Small, strategically placed openings created a chimney effect, drawing cool air in and pushing warm air out for continuous natural ventilation. This was climate control engineered with stone and air, creating a comfortable, stable environment in a land of extremes. Today, architects studying sustainable design look to these ancient principles with growing admiration. The concepts of passive solar gain, natural cross-ventilation, and thermal mass are being integrated into modern buildings to drastically reduce energy consumption. More profoundly, the way these structures are fused with their rugged terrain offers a blueprint for disaster-resistant architecture in areas prone to wildfires, rockfalls, or extreme weather. The cliff dwellings teach a lesson that is more relevant than ever. True sustainability is not about overpowering an environment with technology. It is about a deep, intuitive reading of a place, understanding its rhythms and resources, and building in a way that becomes a natural extension of the land itself. This ancient wisdom shows us that the most secure and resilient home is not one that stands against nature, but one that is thoughtfully woven into its fabric. The Romans' ambition could reshape the very earth, turning entire mountains into sources of gold. To feed their empire's endless demand, they engineered a method of staggering scale, using water not as a tool, but as a titanic force. High in the mountains of Spain and Wales, they constructed massive reservoirs, some holding millions of gallons, channeling this stored power through intricate networks of channels and sluice gates. With a single, coordinated release, they would unleash a catastrophic wave down a hillside. This was Hushing, a calculated deluge designed to strip away soil, vegetation, and soft rock in one furious surge, exposing the precious ore veins hidden beneath. It was a form of hydraulic mining so effective that its scars are still visible on the landscape today, silent testimony to an industrial power that vanished for over 1,000 years. The sheer logistical genius of storing and directing such immense volumes of water speaks to an understanding of hydrology and erosion that was far ahead of its time. Modern mining engineers, facing the immense environmental challenges of their own industry, are now looking back at these ancient operations with fresh eyes. While the Romans' goal was pure extraction, their methods hold unexpected lessons. By studying how they managed water flow and controlled sediment, today's researchers are finding clues for developing more efficient mineral extraction that significantly reduces chemical use and landscape disruption. The principle remains the same, using nature's own force to do the work, but with a modern emphasis on containment and reclamation. This ancient approach challenges a core assumption of our technological age. It suggests that the most powerful solutions are not always about creating new, complex machinery, but about mastering the fundamental forces that have always been available to us, directing them with intelligence and purpose. That same mastery of fire and water extended right into the comfort of a Roman home. Beneath the intricate mosaic floors of a wealthy villa, a hidden furnace breathed warmth through the very stones. This was the Hypocaust, an elegant system of central heating that vanished from Europe for over 1,000 years. Its operation was a marvel of simple physics. A constantly burning furnace, often stoked by enslaved laborers, would heat air and gases. Instead of letting this heat escape, it was channeled into a void beneath the raised floor, which stood on hundreds of short, sturdy brick pillars. The hot air would then circulate through this underground chamber, slowly and steadily transferring its thermal energy to the massive stone or tile floor above. In more sophisticated designs, ceramic box tiles were embedded within the walls, creating flues that would draw the warm air upward, heating the entire structure from the ground up. The floor itself became a vast, radiant surface, warming the room and its occupants with a gentle, even heat that felt nothing like the dry, blowing air of a modern furnace. This luxurious comfort was not merely for indulgence. In the sprawling public bathhouses, it was a public health innovation, creating spaces for hygiene and community even in the depths of winter. The loss of this technology after Rome's fall meant a return to smoky, inefficient hearths and drafty castles for centuries. Today, the principles of the Hypocaust are experiencing a powerful revival in the form of modern radiant floor heating. Engineers are meticulously studying the thermodynamics of these ancient systems, fascinated by their efficiency. The large thermal mass of a stone floor acts like a battery, storing heat and releasing it slowly over many hours, which requires far less energy than constantly reheating air. This ancient insight is now guiding the design of ultra-efficient passive solar homes and low-energy climate control systems. By embedding water pipes within concrete floors, a method directly inspired by the Hypocaust, we can use solar-heated water or geothermal energy to warm our buildings, drastically cutting our reliance on fossil fuels. The Romans understood a profound truth we are only now fully appreciating, that the most comfortable and sustainable warmth does not blow through the air, but rises gently from the ground beneath our feet. The lifeblood of Mesopotamia flowed not in its rivers alone, but in the man-made veins that channeled their power. Across the sun-baked plains between the Tigris and Euphrates, the Sumerians and Babylonians engineered a hydraulic landscape of astonishing complexity. They constructed vast networks of primary canals that siphoned water from the rivers, feeding smaller secondary channels and finally, the delicate ditches that nourished each individual field. This was not a simple matter of digging trenches. It was a high-stakes balancing act that required a deep understanding of topography. The engineers had to calculate a gradient so gentle that the water would flow steadily without stagnating, yet not so fast that it would erode the precious canals. They built robust levees to contain seasonal floods and ingenious water gates made of wood and stone to control the flow with precision. One wrong calculation could lead to disaster, either flooding the fields with silt or, even worse, allowing the land to be poisoned by salt. In this arid climate, constant evaporation would draw salts from the irrigation water to the surface, slowly creating a toxic crust that could render the soil barren for generations. The ancient farmers learned to combat this through a practice of periodically flooding their fields to flush the salts back down, a delicate dance of water management that sustained their civilization for centuries. Today, this ancient wisdom is resurfacing as a critical solution for our own agricultural challenges. Modern center pivot irrigation, while efficient in some ways, can lead to significant water loss through evaporation and runoff. Agricultural engineers are now looking back to the principles of those Mesopotamian canals, designing systems that deliver water directly to the roots of plants through buried pipes, much like the ancient secondary channels. This subsurface drip irrigation drastically reduces evaporation and prevents the rise of salts, mimicking the sustainable practices of the very first farmers. The legacy of Mesopotamia teaches us a profound and urgent lesson. The rise of civilization was not just a social or cultural event, it was an engineering triumph over a hostile environment. Their success and their occasional struggles with salinization provide a timeless blueprint, reminding us that the future of our own food supply depends on our ability to manage water with the same blend of ingenuity and profound respect. A single sheet of Egyptian papyrus holds a story not just in its painted hieroglyphs, but in its very fibers. After thousands of years, these documents remain supple and the ink upon them sharp, while modern wood pulp paper can become brittle and yellow in just a century. This incredible longevity was no accident. It was the result of a sophisticated, multi-step manufacturing process that functioned as a form of ancient material science, a craft that was completely lost and has only recently been decoded. The method began with the core or pith of the papyrus reed. This pith was cut into thin, vertical strips. These strips were not simply laid together. They were arranged in two layers, one horizontal and one vertical, then soaked in the nutrient-rich waters of the Nile. This was the crucial step. The water activated the plant's natural sugars and starches, which seeped out and acted as a powerful, natural bonding agent. The wet layers were then pressed together with immense force, either under stones or in a specialized press. As they dried, the natural sugars crystallized, fusing the strips into a single, incredibly strong and uniform sheet without any need for glue or synthetic additives. The resulting material was both lightweight and remarkably durable, resistant to tearing and the degrading effects of time. Modern scientists, using chemical analysis, have identified this precise sugar-based bonding process. They now see it not as a primitive craft, but as a brilliant early example of creating a composite material. This ancient insight is now fueling a revolution in sustainable material design. Researchers are experimenting with other fast-growing plants, like hemp and bamboo, using similar principles of natural activation and pressing to create strong, biodegradable biocomposites. These new materials can be used for everything from eco-friendly packaging and building insulation to a new generation of archival paper that could preserve our own records for millennia. The Egyptian scribe, by mastering the humble papyrus reed, did more than create a writing surface. They pioneered a model of production that works in harmony with nature, using rapid renewable resources to create products of astonishing durability. In an age grappling with the environmental cost of synthetic materials and deforestation, this 2,000-year-old method offers a clear and elegant path forward, proving that some of the most advanced solutions are already written, quite literally, in the pages of the past. An empire woven together by rope and stone stretched for thousands of miles across the most brutal mountain landscape on Earth. This was the Hypocaust, the Inca road system, a monumental web of highways and pathways that bound a vast territory together. Its construction was an act of sheer defiance against the terrain. Engineers carved staircases into vertical cliffs, cut tunnels through solid rock, and laid stone pavements that followed the harsh contours of the Andes. But the true masterpieces of this network were the bridges. Spanning deep gorges and raging rivers were suspension bridges made not of steel or concrete, but of woven grass. These were not fragile, swaying footpaths. They were robust structures, some wide enough for Spanish conquistadors on horseback to cross in formation, capable of supporting the movement of entire armies and trade caravans. The secret to their strength lay in a profound understanding of natural materials. Builders would twist native grasses into thick cords, which were then braided into massive cables. These cables were woven together into a solid deck, creating a structure that was incredibly lightweight yet possessed immense tensile strength. The bridges were anchored to stone towers on either side of a chasm, and their brilliance was in their flexibility. Instead of resisting the powerful mountain winds and the shifting weight of travelers, the bridge would sway and move, absorbing the energy and distributing the load evenly across its entire woven form. This design was so effective that some of these grass bridges remained in continuous use for over 500 years, a testament to a lost engineering art. For a long time, how they achieved such longevity was a mystery. Modern analysis of the few remaining examples and historical records has revealed their secret. It was not just the material, but the specific, intricate weaving technique that created countless redundancies. If one grass fiber broke, the load was instantly transferred to its neighbors, preventing a catastrophic failure. This principle of distributed load and redundant strength is now a cornerstone of modern engineering. Today, this ancient wisdom is inspiring a new generation of pedestrian bridges and emergency structures. In areas prone to earthquakes or where rapid deployment is needed after a disaster, engineers are designing bridges using synthetic cables that mimic the flexible, redundant weave of the Inca bridges. These structures are resilient, adaptable, and remarkably strong, proving that the most durable connection across a divide may not be a rigid beam but a flexible weave. The Hypocaust was more than a road. It was the circulatory system of a civilization, demonstrating that the ambition to connect, to trade, and to communicate across vast distances is a deeply human drive. Its legacy, written in grass and stone, challenges our modern obsession with permanence and brute force, offering a quieter, more elegant lesson in resilience. True strength, it seems, is not about refusing to bend, but about knowing exactly how to move. The Roman siphon was a feat of engineering that moved through the earth, not over it. When an aqueduct channel met a deep valley, Roman engineers avoided the immense cost and labor of building a towering bridge by taking a daring downward path. They constructed a sealed lead pipe system that plunged down one slope, crossed the valley floor, and then climbed steadily up the opposite side. This was not a simple downhill run. It was a brilliant manipulation of a fundamental law that water in a sealed system will rise to the same level from which it started. The tremendous water pressure that built up in the descending pipe was the very force that pushed the water back up the far side, allowing it to rejoin the channel at nearly its original height. This was not a primitive workaround. It was a masterful application of fluid dynamics, a technology that required an advanced understanding of pressure, pipe strength, and hydraulic gradients. The knowledge to design and maintain such a system faded for over 1,000 years after Rome's decline. Today, hydraulic engineers are looking back at these inverted siphons with a newfound respect. In remote, mountainous regions where electricity for pumps is unavailable or prohibitively expensive, the Roman approach offers a powerful, gravity-fed solution. Modern versions use durable plastics and advanced valves, but the core principle remains identical, using the landscape's own topography to create pressure and move water across impossible divides. This ancient method challenges our instinct to always build higher and bigger. It reveals that the most elegant solution to a topographic barrier is sometimes not to bridge the gap, but to embrace the depth, allowing the fundamental forces of nature to do the work for us. A bridge of iron chains spanned a river in ancient China, a sight that would have defied contemporary understanding. While other cultures relied on rope or wood, Chinese engineers made a bold leap into a new age of materials. They created suspension bridges using massive, hand-forged iron chains, each link a testament to a lost metallurgical art. the process was extraordinarily complex. Blacksmiths had to forge individual iron links, each one perfectly shaped and then interlocked with its neighbors into a continuous, flexible chain of immense strength. These chains were then anchored to massive stone piers on either bank, supporting a wooden deck that allowed travelers to cross chasms that were previously impassable. The technology was so advanced that it allowed for spans far longer and more stable than any rope bridge could achieve, conquering geographic barriers with unprecedented grace. For centuries, the precise methods for creating and erecting these chain bridges were a mystery, their secrets buried in fragmented texts and the rusted remnants of the bridges themselves. Modern archaeological work has painstakingly pieced together the puzzle, revealing a sophisticated understanding of load distribution and metalworking. Today, this ancient innovation is capturing the imagination of bridge designers working in some of the world's most challenging environments. In remote mountainous regions or areas prone to earthquakes, building conventional bridges is often too costly and logistically difficult. The principles of the ancient Chinese chain bridge, with its lightweight, flexible, and incredibly strong design, offer a perfect solution. Modern engineers are using high-strength steel alloys to create cables that function on the same fundamental principle, allowing for the construction of durable footbridges that connect isolated communities without the need for massive, disruptive infrastructure. The legacy of these iron chains is woven into the very fabric of our modern world. They represent a pivotal moment in engineering history, the first bold step that would eventually lead to the majestic steel suspension bridges we know today. This ancient method demonstrates a timeless truth that the most profound breakthroughs often come from looking at a familiar problem through the lens of a new material. A whisper on the stage could be heard with perfect clarity in the very last row, high above. This is the enduring mystery of theaters like Epidorus, where sound travels not through wires or speakers, but through stone itself. For years, the sheer perfection of this acoustic phenomenon baffled experts. How could a single unamplified voice carry so far and so clearly over the noise of a crowd? The answer was not in some lost device, but in the very geometry of the seating. Recent research using sophisticated computer modeling and acoustic scans has revealed the secret. The stepped rows of limestone seats are not merely stairs for spectators. They function as a sophisticated acoustic filter. The rough, porous texture of the stone absorbs the low-frequency rumble of the audience, the distracting background noise that would normally drown out a performance. At the same time, the precise angles and corrugated surfaces of the steps act as a perfect reflector for the high-frequency sounds of the human voice, catching each syllable and projecting it upward in a clear, focused wave. This was not a happy accident of architecture. It was a deliberate and brilliant feat of acoustic engineering. The entire structure was a precisely tuned instrument, meticulously designed to celebrate the nuances of speech and song. Today, this ancient wisdom is resonating in the designs of our own modern spaces. Architects and acoustic engineers are studying these principles to create new amphitheaters and concert halls that rely on natural sound amplification. They are integrating textured surfaces and calculated angles to reflect sound perfectly, reducing the need for complex and expensive electronic speaker systems. This rediscovery shifts our entire perception of these ancient spaces. They were not just monuments to be seen, they were immersive experiences to be heard, demonstrating that the ancients designed for the ear with the same profound care they gave to the eye. The shimmer that adorned a pharaoh's mask was not merely a layer of gold, but a whisper of metal thinner than a human hair. Egyptian artisans perfected the craft of gold beating, transforming solid ingots into ethereal foils only microns thick. This was not a simple hammering process. It was a ritual of material transformation, a multi-stage dance of patience and force. The gold was first hammered into a small, thick sheet, then carefully cut and sandwiched between layers of specially prepared animal skin. This protective packet was then subjected to hours of meticulous, rhythmic hammering. The craftsman had to possess an intuitive feel for the metal, knowing precisely when to stop and repackage the foil to prevent it from tearing under the immense distributed pressure. The result was a material of breathtaking consistency, a perfect, molecularly thin skin of gold that could be applied to wood, stone, or papyrus, creating objects that seemed to capture and hold light itself. The secret to achieving such uniform thinness without modern precision rollers was a complete mystery, a lost art buried with the artisans themselves. Modern materials scientists, through the field of experimental archaeology, have painstakingly recreated this process. They discovered that the specific type of animal skin used acted as more than just a cushion. Its unique fibrous structure and natural lubricants allowed the gold to spread in a perfectly controlled, plastic flow under the hammer's blows. This ancient method was, in essence, a form of room-temperature nanofabrication. Today, this rediscovered wisdom is sparking innovation in our most advanced industries. The challenge of creating ultra-thin, uniform coatings is central to modern technology. In electronics, such coatings are vital for efficient conductors and sensitive sensors. In aerospace, they provide critical thermal protection with minimal weight. In medicine, they can be used to coat implants for better biocompatibility. The principles of the gold beater, using layered materials and controlled force to manipulate matter at the smallest scale, are guiding the development of new physical vapor deposition techniques. These methods aim to create perfect thin films without the high energy costs of traditional manufacturing. The legacy of these ancient craftsmen redefines our understanding of their work. They were not just decorators, they were the first nanotechnologists, proving that the drive to master material at the most fundamental level is a pursuit as old as civilization itself. This recurring pattern of rediscovery reveals a profound truth about human innovation. We have long viewed history as a straight line, a steady march from primitive tools to sophisticated technology. Yet the evidence before us tells a different story. The separation between ancient and modern engineering is an illusion, a temporary gap in a continuous conversation. Both are united by the same fundamental principles of physics and material science, and both are driven by a deep, intuitive understanding of the natural world. These are not separate schools of thought, but different chapters in the same endless book of human problem solving. The concrete that heals itself, the crystal that finds the sun, the woven bridge that dances with the wind, all speak to a universal language of ingenuity. This cyclical nature of knowledge, where brilliant solutions are found, lost to time, and then found again in a more refined form, completely challenges our linear narrative of progress. It suggests that the wisdom of the past is not a graveyard of obsolete ideas, but a living library filled with untapped potential for the very problems we face today, especially in sustainability, resilience, and efficiency. What we are witnessing now is the birth of a new, hybrid engineering philosophy. It is a vibrant dialogue between the ancient artifact and the modern laboratory, a synthesis that respects the profound insights of our ancestors while leveraging the analytical power of our current technology. This partnership does not look backward out of nostalgia. It looks backward to move forward, mining the past for the fundamental keys that can unlock a more elegant and enduring future. The promise of this synthesis is vast, hinting that the next great leap in engineering may not come from inventing something entirely new, but from understanding at the deepest level what has already been proven to work. From self-healing concrete to acoustic filtering theaters, these 25 ancient methods reveal a stunning truth. Our ancestors were not primitive, they were pioneers. Their innovations, only now being fully deciphered with modern science, represent a vast library of sophisticated knowledge that was tragically misplaced for centuries. This journey of rediscovery is far more than a tribute to the past. It is an active, vital contributor to our own future, providing elegant and time-tested solutions to the very problems of sustainability and resilience we grapple with today. The loss of this knowledge was a profound setback for humanity, a dark age of forgetting, but its recovery is a triumph of curiosity, a reminder that human creativity is a boundless and cyclical resource. We are now in a unique position to blend ancient wisdom with modern analysis, creating a powerful new hybrid philosophy for innovation. Let this exploration change your perspective. See the ancient world not as a static museum of artifacts, but as a living, breathing library of brilliant ideas. Every crumbling wall, every silent mechanism, holds a story and a potential solution waiting to be checked out and read with fresh eyes. We would love to hear which of these ancient methods captured your imagination most powerfully. Share your thoughts in the comments below and subscribe to continue this journey of discovery with us.